Okay, hey, let's look at section 6.2. It's volume of solids with known cross sections. There's a little bit different way to get volumes, and what we've known up to this point is we revolved a shape around an axis. So let's say our curve was, we've done a lot of y equals x squared, haven't we? And revolved, this shape about the x-axis. We've also revolved it around the y-axis, and we've found that it gives us, some sort of 3D image or volume. So what we're working on today here is we're going to take a plane figure where we are creating our bounds with, say, two functions. So in this case, I've got g of x and f of x. And we're going to take that and fill it with cross-sectional pieces. In this case, in this one, you can see they are squares that's filling the area. So as my distance between the curves gets wider, my squares, well, it's not a very good square, is it? My squares are going to get bigger and bigger to match that distance across the curve. Okay, and you can see by the shape of this, as this increases, here's kind of the ribbing along the top of my shape, and then eventually it'll go back down and become smaller and shorter. So how do you calculate this volume? Oh, let me show you an animation first. So I've got one with the squares. So here's the idea. There's our base area, would be what we're starting to fill, and we're filling this one with squares. So as the base becomes wider, the squares become taller and wider as well. And you can see this 3D image now coming through. It's going to fill all the way over to that y-axis. And this is the volume we want to cover. Okay? Let me get back and back. So if it's squares, let's investigate squares. So I have this square that's going to span my base region. And that distance between my base region, if this is my function g of x, write it on your paper if you cannot see it. This is f of x. Then the base length here, across there, would simply be top function minus bottom function. And since it's a square, the height of my square would be a matching distance as the width across the base figure. Now, in order to calculate the area of a square, it would be area equals, well, we know squares to be length times width, don't we? And in this case, area is going to be f of x times, no, it's minus there, isn't it? Sorry, that's a minus, and it's intended to be a minus. F of x minus g of x times f of x minus g of x. The width and the length were a complete match. Well, we can reduce that to be f minus g, I'm going to leave off the of x, quantity squared. And that's the base figure. Now, that base figure has a really tiny depth to it so that we can pick up volume. So I'm trying to draw a depth here. That depth would be a dx depth. So it's got a little bit of depth to it, infinitesimally small, some change of x. If all these cross-sectional pieces were added up, they would total the volume. So I want to come in with volume, and the volume statement for cross-sectional area is simply A to B. These would be x values because I'm going to use my x ones. And it's the area in terms of x multiplied by dx. So area times thickness give us volume. So if I follow my pattern here, it's going to be from A to B, those intersection points of my curves. And then for squares, it's going to be f of x minus g of x quantity squared dx. And that's all that's to it. Let's look at right isosceles triangles. And in this case, I can see that this right isosceles, so I've got equal, equal, is sitting on the leg. And that does make a difference. So this is with a leg spanning across the f and g function. So this is my x-axis. This is kind of tilted, sort of funny. X-axis, y-axis, and this is my f of x function, which rides above the g of x function. So label those up. Now, for our right isosceles triangle, we've got this right isosceles laying in there. This distance across the base of my triangle is simply the distance from f of x across to g of x. So this becomes an f minus g. And since it's right isosceles, the height of my function is equal to f minus g. The hypotenuse is not even going to figure into us on this. So find the area of the triangle above. We know the area statement for a triangle is 1/2 base times height. So area equals 1/2. My base was f minus g, and my height is f minus g. Well, that's awful like the triangle, or the square. And matter of fact, if I completed this, it's a square, isn't it? But we have half of a square. Oh, we have half of a square. Volume equals 1/2 the integral of f minus g if it is a right isosceles triangle with a leg on the base, where a leg is spanning the base. With, please add this to your notes, with a leg spanning the base area. Okay? What I'm generating here are just some very generic formulas that will work for the different shapes. And believe it or not, it's not too hard to remember. Squares have a coefficient of 1. Right isosceles triangles with the leg spanning the base has a coefficient of 1/2. Notice they both have f minus g quantity squared. There we go. Let's move on. How about if it's an equilateral triangle? Equilateral triangles are a little bit more difficult. This is my x-axis. This is my y-axis. This is f of x, since it's my higher curve. This is g of x. So now I want to come in and calculate the distance across the curves. And then I've got these equilateral triangles in here. So for equilateral triangles, I don't have to specify that it's on a certain side because all 3 sides are congruent, aren't they? So I just drew in that congruent idea. The distance from one side to the other here is the spanning between the 2 curves, which would be top curve f minus bottom curve g. Parentheses around that. All right, so we got that notion. Now, let's go back to geometry class when you worked with special right triangles. I knew I had an equilateral triangle, 60, 60, 60 for their angles. I'm going to drop in a perpendicular bisector, which will bisect my angles. So now I'm in a 30, 60, 90 on the right side as well as the left side. This little portion here ends up being 1/2 the total distance across the base. So I'm now at 1/2 f minus g. I'm doing that so I can calculate the height of my triangle. This height of the triangle, in a 30, 60, 90, remember how those went x root 3, twice x. That was the pattern for a special right. Helpful information. So now I know that my height is simply the x value, which happens to be 1/2 f minus g multiplied by square root 3. that would simplify down to square root 3 over 2 of f minus g. All right, keep those figures in your head. Well, keep them on your paper, actually. Let's see if I can slide. Now let's find the area of the triangle above. Area of a triangle formula, basics, 1/2 base times height. Area of an equilateral triangle. We have our 1/2. My base, total distance across the base, is that f minus g, isn't it? The height was up here, and that was a root 3 over 2 times f minus g. Box that out if you want. So this was height, this was base, wasn't it? Base times height, and then a 1/2, right? Okay, simplify this, and we get area equals 3, square root 3 times 1 is square root 3. 2 times 2 is 4. And then I have f minus g times f minus g. That gets me an f minus g squared. So if I added up all of these equilateral triangles that have a thickness of dx, I would have the integral from a to b. I want to put square root 3 over 4. I want my coefficient out front. F minus g quantity squared. If you flip your page over, we have seen this pattern before, haven't we? F minus g quantity squared. Now I just have a new coefficient for an equilateral triangle. And I think you can see how we came up with that. Root 3 over 4. Okay, moving on to another figure. A semicircle. So once again, this is my x-axis. This is positioned as the y-axis. This is f of x. This is g of x. The distance across is f minus g. So in this circle, my diameter, and this is important, the diameter is equivalent to the distance across the base, which is f minus g. Now I want to find the area of a semicircle, 1/2 pi r squared. That means I need radius. Well, how far is it across? Well, it's half the distance for the radius, isn't it? The radius will equal 1/2 of the diameter, f minus g. Okay, that's all I need. I need radius to calculate the area of a semicircle. That's going to give me 1/2 pi times 1/2 f minus g. I'm substituting in my radius. It gets squared, correct? Let's square that. We got 2 lines to finish up here. So leave a little space. Squaring 1/2 makes 1/4. F minus g quantity squared. Oh wow, we've seen that before. Things getting squared. Now let's multiply. Pi, or 1, pointing at 1. 1 plus pi plus 1. That gives me pi on top. 2 times 1 times 4 gives me 8 on the bottom. F minus g quantity squared is the area of a semicircle. Okay, so the volume is equal to pi over 8 integral a to b f minus g quantity squared dx. What do you notice about the integral defined formulas for finding volumes of solids with certain cross sections? That we always utilize f minus g quantity squared. So in fact, it's really based on the area of a square cross section, isn't it? And then those coefficients just tell us what part of that cross section we have. So based on area of a square cross-sectional piece. Hopefully this has been sort of easy to understand. There's a couple more that I'd like you to jot down. Well, those are some answers. This will be the homework working with this particular one, and you just got to walk through all the others. I'll let you see the other answers so that you can see if you're getting them right tonight as you work through your homework. Okay, like I was saying, there are some other ones I would like to discuss with you, and one of them is an isosceles triangle on the hypotenuse, where the hypotenuse spans the field. So let's lay out y and x. Once again, let's give ourselves f of x, g of x, and we want to span across this with isosceles right triangles with the hypotenuse across here. So the area of that would be something similar to this, wouldn't it? Where these are 45 45s. And that's a little harder to work with. This becomes f minus g, the distance across our two curves. Drop in a perpendicular bisector, and in a 45 45, we know we have equal, equal, and then this becomes the new hypotenuse for us. This is x, x, and then it was x root 2 if you just want to remember that from the past. Now, how far is this? This is 1/2 the total distance across, so 1/2 f minus g. That means this x is also that same distance. So the area formula for this triangle is a 1/2 times the base, which is my blue figure, f minus g, times the height, which ends up being 1/2 f minus g. Oh, so this ends up being a pretty easy little formula, doesn't it? It ends up being 1/4 of f minus g quantity squared. And that is if you have an isosceles right triangle situated on the hypotenuse spanning the distance across the two curves. 1/4 is, so the volume equation would look like 1/4 a to b of f minus g squared dx. Alrighty? That covers the basics of it. Shouldn't be too bad. Do that next sheet for homework, and I think we'll work in class on this one. So there you go. Have a great day, you guys.